Hi, welcome to Oldenburg University. I'm Jessica and currently I'm doing my PhD at the Department of Chemistry. But it's getting quite cold out here. Let's go inside so I can show you our UHV lab and tell you something about my recent work. So this is our UHV lab. Behind me you can already see our 3 UHV systems. They are all 3 connected by a park station where we can also store our samples in UHV. In each of our UHV chambers we have a base pressure below 10 to the minus 10 millibar. For comparison, this is around 13 orders of magnitudes lower than out here. Under these conditions we have around 1 hour to do our measurements. If we would take the sample out of the UHV chamber and do the same measurements here, we only have around 1 nanosecond.
The used sample looks like that. So we put the Rutile Titania single crystal on a sample holder and insert it into the UHV chamber, as you can see here. The surface termination is called a 1,1,0 termination, which describes to the experts that oxygen atoms are arranged as rows with grooves between them, sitting on a layer of alternating titanium and oxygen atoms. Before each measurement, the sample must be cooled down to 100 Kelvin. To reach such temperatures, we insert liquid nitrogen into the manipulator. In the manipulator is a copper pipe which goes all the way down to the sample holder. Afterwards, we can start preparing the sample. First, we clean it by argon ion bombardment and subsequent annealing at 880 Kelvin to get rid of contaminations. Now we are ready to start. To identify possible desorption and reaction products of 2-propanol, temperature-programmed desorption spectroscopy is used. Here, we dose a specific amount of 2-propanol at 100 Kelvin on the sample and heat it up with a slope of 2 Kelvin per second to 880 Kelvin. All the heating is done in front of a mass spectrometer. By using a Follner cup in front of the mass spectrometer, it is possible to precisely detect only molecules that desorb from the sample. So temperature-programmed desorption spectroscopy showed me that in case of 2-propanol, a reaction to propane and propene takes place. They both desorb at the very same temperature of 550 Kelvin. Furthermore, the propene formation can be suppressed by applying UV light. In the presence of oxygen and after UV irradiation, acetone is formed indeed and can be detected at around 200 Kelvin. To gain further information, for example on the reaction mechanism of both reactions, polarized Fourier transform infrared reflection absorption spectroscopy can be performed. Here we again dose a specific amount of 2-propanol on the surface at 100 Kelvin and then get the sample into the spectrometer at the bottom level of the chamber. These measurements showed that propane and propene have different precursors from which they dissolve. Furthermore, acetone forms with the dialide species as intermediate. The same photochemical conversion from 2-propanol to acetone was also observed by our collaborators from FAU Erlangen-Nürnberg in liquid phase by using rutile powders as catalyst.
If you now get interested in the reaction mechanism of the conversion of isopropanol on titania, have a look at our paper. Here we especially want to thank our collaborators from Erlangen-Nürnberg, Fabian Weithas, Olaf Brummel and Jörg Libuda, and also all members of the Physical Chemistry 1, and Thomas Teusch and Thorsten Klüner for support with theoretical calculations. Thank you.